There we go. Yay. All right. What are we doing? What are we going to go to today? Well, today we're going to talk about programs. We're going to talk about the next level up. So we've talked about like the low-level hardware, and we've talked a little bit about the operating system itself, and we're going to start diving into exactly how the programs get created. We're going to do that by looking at kind of the tool chain in the pipeline. Now, some of you have done this inadvertently before. You get that kind of instruction says, hey, to build a program, you write it in this language, and here's all the things of this language, and then you run it through this tool and that tool, and all of a sudden a program spits out. We're going to dive down into a little bit lower level and play with a couple tools, and hopefully, if we're lucky, we'll be able to let you play with some of the different programming languages as we go. So I'm going to get going here, and we're going to start looking at some of the possibilities we have for building programs. Right? Now, we've talked about this a little bit before, and let me just start to do this. We have a bunch of tools that have evolved mostly for historic reasons over time. And for the most part, the tools that we've used to build programs kind of break down into compilers, languages, the shell to tie them all together, and all done from the command line. So we're going to do a little bit of that today. We're going to play with it a little bit. I promise you we won't make you write anything hard or difficult. I'll walk you through it. I won't promise you won't see programming languages you haven't seen before, because you will. And the big thing here is to recognize that they all kind of try and do the same thing. And that is, we got to solve a problem. We don't want to write machine code. We're probably not real friendly with writing assembly language. So we would like to write something that's a little bit easier to solve our problems in. And early on, this is how computer science really got rolling, is once we had machine code running on a processor, somebody decided that writing machine code sucked. And so they invented an assembly intermediate language, and that assembly language could be run through a program that was written in machine code, but you only had to write that machine code program once, and it would turn assembly language into machine code. Cool, that's one step. And then the next step is, well, the assembly language isn't much better to write stuff in, so maybe we should write stuff in another language, something that's a little bit higher level than that. And maybe I could write a program in assembly language that would take my alternate language, my new language, and assemble it into assembly language where it could run through my existing assembler to turn it into machine code, which is kind of exactly what happened. Running these programs, building these programs, involved having to have some functionality in the operating systems to run them in the first place. And so one of the first programs people wrote was what we call a shell program. And we're going to use a couple of them today. The command line tools in your Windows computer are just another shell program. It's just a shell. The operating system runs it. The key difference with shell programs is they give you access to all of the operating system by typing in commands and allowing those commands to execute. Some shells have built-in commands. Some shells just let you run executables. So we're going to play with a little of both of those. The key thing that every shell program has to do is it's going to take some parameters on the command line, whatever the user types in, and it's going to parse those or break those parameters into separate pieces. And the typical way that we separate those parameters is by putting spaces in between them. makes for a nice environment. It also means that as we go later into development, time-wise, that is, developing tools and files and programs, adding spaces to file and folder names becomes really, really problematic, because to most applications that have a command line version, the spaces in your file name are indistinguishable from the spaces between parameters. And so one of the first things we get to is, for most programmers, is thou shalt never use spaces in file names or folder names ever again. And they will cause you nothing but grief. And then amidst all of that, Microsoft popped out this Windows thing in the late 80s, and the first thing they did is create a folder called Program Space Files, when you were just like, really? So this created some issues we'll have to deal with. We're also going to get into a little bit of working with streams or pipes of information. All of our programs adopt some terminology from the environment around us. In other words, when developers first built these programs, they named things based on things around them. Your computer boots itself. Why does your computer boot itself? Where does the term boot come from? Any ideas?
Like pushing them along, like moving them forward.
Close, but not. Right? When cowboys get up in the morning, what's the first thing they do?
Put on the boots.
They pull on their boots. They pull them by their boot straps.
Oh.
The little loops on the sides of your boots. Okay? Everything to do with computing is based on some kind of notion like that. You keep your files in folders. Well, that came from old school file drawers. The files, what could they have in them? Well, anything. We don't know. You have to open the file to find out. When we talk about data, it's going to flow from a source to a sink. Think about your sink. It's got a tap in it. The water comes out one end and goes down the drain. Sources and sinks for information. So when we talk about how our applications work and how they work on the command line and parameters and stuff, we often refer back to kind of these colloquial ideas of the way people first put things together. And these days, a lot of those things have just been lost over time. People haven't recognized that every piece of software that's out there was written by a person or a group of people. And to understand the problem that they were solving, they would relate it to things they already knew how they worked. So it's not rocket science. It's just kind of trying to get your head in the headspace of the programmer that wrote the program you're trying to use and go, okay, if I were trying to build this, what would I call this? How would I refer to this? How would I think this works most naturally? When it came to writing these programs and solving these problems, every different kind of problem, naturally, everybody had a different opinion on which programming language or what a good programming language would be to solve their problem. If you came from a mathematics background, you would want, a lot of variables and parentheses and brackets all over the place. If you came from an English literature background, you'd want something that was very verbose and easy to type and read. If you came from an engineering background, you might want heavy-duty numerical analysis going on. Well, software developers try and cater to all of those things by evolving different languages to solve different problems. And those different problems often show up in terms of different levels of complexity and size for applications. In some cases, the problem that we're solving is really, really small, but really complicated or really time dependent. Things like device drivers and real-time controllers. the guy writing the controller for the anti-lock brake system in your car, or for the kill switch on the sawmill 6-foot blade, probably have to pay more attention to timing than anything else. Whereas the printer driver for your printer on your computer really just needs to take some generic commands from the operating system and turn them into specific commands for how do I tell your printer to print a page, and what does the page look like, what format's it in. As we step up, the next level of kind of complexity is we get to operating systems and compilers. Again, fairly complex programs that aren't necessarily huge, but the level of complexity in, say, a compiler, if you were writing a compiler, to be able to read a language text in, parse it into individual tokens, break those tokens up into some sort of semantic meaning, and then based on those tokens, generate assembly code from them. You know, how do you turn a for loop into assembly code? It's a fairly complex process, but not massively huge. And in that mix, I've thrown the mobile applications and game developers, because we have this weird place when we're building games that's halfway between really low-level programming, when we start talking about rendering and shaders and drawing triangles and polygons, and the linear algebra behind them, and the matrix math that we're going to do, and dot products and cross products and all that kind of good stuff that you guys are all familiar with, right? And then on the other end, I'm writing general purpose AI algorithms for how does a collection of enemies move in relation to where the player character is, based on some stimulus in a fake environment that I'm simulating in my game application. So they're kind of these weird different levels of detail complexity. And game programs are not typically huge. They're in the, up to 1 million lines of code kind of range. And you can get used to thinking about that as not gigantic, but not small. And then finally we have, what I phrase here as applications or tool programmers or enterprise developers. In British Columbia, we have an entire government-run organization for insuring cars, car insurance. Now, this is not hard or complex software to write. It involves filling forms in. But there's over 3,000 terminals that use this software simultaneously, and all have to talk to a central data store on an hourly basis that needs to be 100% accurate and up to date all the time. And one can only imagine the number of screens one of these agents has to go through to issue your insurance. Look, make sure you don't have any outstanding bills that have to be paid, figure out what kind of vehicle you're driving, how much coverage you get, what you're entitled to. It's not overly complex. It's just a set of rules that the insurance company wants. The software is really a bunch of forms. It's not hard to make. But it's really, really large. I mean, there's a lot of it. Think about Amazon. Amazon's website is fairly straightforward. It's a scrolling list of images in a grid, a couple sidebars and things to the side. But think about how many different tabs and widgets and pages and details and purchasing that all have to work with each other. It gets really, really huge. So necessarily what people do is, as they started to evolve programming languages, the programming languages evolved based on the kind of problems people were solving at the time. So we have to kind of figure out what are the best tools. And that's where I want you thinking about programming languages as nothing more than tools. It's a bunch of screwdrivers and hammers in a toolbox. The more of them you know, the better off you are. C# is not the only tool in the toolbox. It's not even the best tool in the toolbox. But there are certain problems that C# handles way better than any other language or tool out there. And when we get to the pipelines course in term 4, we absolutely will exploit that. Okay. Likewise, C# sucks rocks for doing web programming. It just absolutely hasn't got the tools you need to work on the internet. Java is just dog slow, but it's really easy to read. A nice light book. And a book is key there. And its predecessor, COBOL, is even more verbose. Many of you have probably encountered things like Visual Basic before. It's the language that Microsoft embedded in all their Office tools. And it's a derivative of one of the first languages ever built, designed predominantly to teach people programming. Which, incidentally, the early versions of BASIC didn't have half of the typical programming constructs that we use day in, day out. Like functions. So, all of these languages evolve based on the need for them. Right? And so the main goal that we have is to solve a problem. We need to identify that problem. We need to know what the problem is inside out and backwards. In a commercial world, as opposed to in a game development world, there are people who specialize in this, and they're called requirements analysts. And what they really do is go and spend their time learning some person or some business's actual problem or job in an effort to build a system and design a system that can solve their problem. In a game application, you got to ask yourself, what's the problem you're solving? And think about that for a second. What does a game application solve as a problem?
Solve the demand for a certain item or a certain product?
Kind of. I have a very specific definition that I use for what a game application really solves. Right? And for me, a game application has one purpose. And that purpose is to get an emotional response out of the player. I need to do something to make the player feel something. Whether it's happy, whether it's excited, whether it's skilled, whether it's frustrated. I'm trying to get an emotional reaction out of people. And if all of the things we do in terms of game design and game development are geared at that one thing, when a player picks up my controller, I want them to have an experience. I'm going to build some sort of simulation. They're going to interact with the simulation, and I want the feedback from the simulation to make them feel something. What they feel is up to what the game is that I'm looking for. You know. Has everyone played Halo?
I played Halo 3.
Okay.
I played the newest Halo a little bit here and there.
So you've got a rough idea of what Halo is like. And Halo has a very typical model, but it actually fulfills this goal really well. And a couple more. And I always use it as the same example. And it's the thing I call the oh shit moment. And that's that moment in the game when you realize something isn't exactly what you thought it was. And for me, it happened in Halo, in the very first version of Halo, because as the game goes, it was just a first-person shooter adventure game, and I'm playing through, and I'm getting better the more I play, and I'm collecting up items, and I'm collecting up guns, and I'm getting good with the different guns. And you get to about a third of the way through the game, and you kind of feel like, I've seen every gun, I know how all the things work. I'm just going to follow through these beautiful environments and figure out how to open the doors and get to the next space and get the next thing until I get to the end of the adventure. And I was feeling pretty proficient with that, and I came around one corner, and all of a sudden I met the Flood. You know what the Flood are in Halo? They're a bunch of little spider bots, and there's easily 1,000 of them or more on screen. And that oh shit moment hits you when you go, I have 220 rounds in the gun, and there's easily 1,000 of these critters coming at me. And there was nothing you could do. You were just... And I realized at that point that they had created an emotional reaction on me. They had built me up to be really confident and then threw a challenge at me that forced me to think completely outside of the box. And that's that kind of emotional reaction that games are supposed to try to elicit from people. That's what you're shooting for. Okay? Now, you're not always going to hit it. You're not going to hit it in every moment. And that's why game development is a challenge. So how we tie this into this engineering kind of process, and this engineering process is universal across all types of engineering, including software engineering, is identify your root problem or your goal. Our goal is to get an emotional response out of people. Then I'm going to propose a solution that in the bigger sense is your game design. How the hell am I going to get that to happen? Right? Then I need to evaluate or test that solution or prototype things. I need to build sub-pieces, typically the hardest pieces, first, and put them in front of people and test them. And not be afraid to go, wow, that was an abysmal failure. Throw that away. Oh, look, that worked better than I expected. We'll do more of that and less of this. Once we have these solutions, we start to cobble them together and we start to iterate on these solutions. We merge them together, we test again. We merge them together, we test again. And those last 4 steps you repeat until you run out of time or money. Right? Evaluate, test, iterate, build, test again. Iterate, build, test again. And there's no end to it, which means you're constantly going to be updating things. Software has bred some tools to make that easier, and programming languages are amongst them. The tool of a programming language lets us evaluate and test a solution by building an electronic file of source code and turning that source code into our solution that we can execute and put in front of a person and run. And if it doesn't work, we change the source code and do it again. Which means when you're building software, it's not like I wrote this thing and therefore I can't ever delete it again. It's exactly the opposite. I wrote this thing and it kind of works, but now I have a better way. So I'm going to rewrite it. And it still works, but I think of a better way. So I'm going to rewrite it. And we want our tools and our languages to make it easy for us to do that. So when we're creating programs, we want to create them in programming languages that make it easy for us to edit, modify, and change things so we can follow this iterate, build, test model. And it gets us to a better solution than just a one-off, yeah, this is the way things should work, and you should just learn how that tool works. Which unfortunately is still how a lot of software is constructed. Now, most programs are built with the same kind of basic premise as how they put together. And it kind of all started with this one main programming language, that is. And most of the development tools, the compilers that people built for these programming languages, they gave away for free. Part of the reason for giving them away for free, hopefully, is obvious, and that is if you come up with a great programming language that solves a specific kind of problem, and you want people to use your programming language, what is the best way to get them to use your language? Well, it's to build great tools and give the tools away for free. The more free tools you have, the better it is to work with. Now, you guys have all worked with Visual Studio Code and Visual Studio Community at this point. One of them takes half an hour to load up, one of them takes 2 minutes. One of them has a significant amount of functionality that the other doesn't have. They're geared towards different kinds of development. And they each have strengths and weaknesses. And rather than getting into kind of a religious war over this is better than that, we kind of take them at face value and go, there are times when one tool is going to be better than the other. But one thing is consistent about them for development tools, they are free. Visual Studio Community is free. Because if it's not, then people don't use Microsoft's tools to build applications. They use other tools. They'll find free tools. Now, you guys have been playing with Jeff and playing with Maya. Maya is what the industry uses. It's also a paid tool. Right? There's an alternative to Maya called Blender. Nobody in the industry uses Blender. Blender is free. Why don't people use Blender? Well, it just hasn't evolved enough yet to the point where it can replace all of Maya's functionality in a way that all the people that know how to use Maya can jump into it and be productive day one. So it's not like that stuff hasn't happened. They just haven't caught on to this programmer mentality yet. Now, if most of the tools are free, that means you can access them and get them. Now, a lot of them are what we call open source these days. And that means the developers or the programmers have posted the software somewhere where you can see the original source code. And they kind of took their hands off and said, I'm going to give it away, but don't ask me to support it. I'm not going to have to maintain it or bug fix it. It is what it is. Take it or leave it. It's free. Right? Well, one of the first ones that kind of started this is one of the first programming languages ever. And it was developed by engineers. And you have to remember that when they developed these programming languages in the late 1960s and early 1970s, the only people writing software were engineers. There was no such discipline as computer science. It didn't exist. So these engineers know what? Anyone got an engineering background? Friends who are mechanical engineers? Nope. You know what a slide rule is? Don't worry, they don't teach that anymore. Basically, engineers have one really big strength, and that is mathematics. Engineering is applied mathematics. Whether it's calculus or linear algebra or just plain old algebra, applied mathematics. In particular, engineers have a wealth of formulas for doing all sorts of kinds of problems. So one of the first programming languages was to solve engineering problems. And of course, it was the formula translator, also known as Fortran. Okay? And much like assemblers would take assembly code and turn it into machine code, a Fortran compiler takes Fortran code and turns it into assembly code. So if you write a program in Fortran and you compile it and then you assemble it, link it together, it should run on the machine in which you're building it for. Now, modern Fortran is a little different than the original versions of Fortran. The original version of Fortran, parsing every statement for the compiler was a bit problematic. They didn't really understand how well to do this, and they had to do it by writing an assembly language program. So the way they did it is they tried to make it easy on themselves. When they designed the language with some interesting properties. The first interesting property is Fortran is very column-centric. Columns 1 to 5, you can put labels in. Column 6 must be blank. That means character 6. You line up every character. Okay. Columns 7 to 72 are your statement, and you cannot go past 72. That was the end of the line, period. Okay. Now those labels aren't like text labels, they're numbers. So you can put a statement in a line, but if you wanted to go back to it again, you'd have to give it a number and tell it to go back to that line number. Now, that sounds really weird, and probably the easiest way to do it is to, literally actually do it. So what I'm going to have you do right now is go ahead and refresh Moodle. What you'll find there is there is a Fortran emulator. Looks kind of like this. Now, what you're looking at is the 1995, which was the latest and greatest Fortran. That's right, Fortran hasn't been updated since 1995. The first version of Fortran came out in 1977. To this day, Fortran is still one of the fastest languages for processing formulas. It is, however, a little bit cryptic to write. So maybe if you can try and follow along, we're going to do a different program than Hello World. I mean, you can try and run the program. You can hit execute. And it runs the Fortran compiler on the command line. And then it executes what it generates. Now that command line says run GNU Fortran. Use the standard 1995 version of Fortran. Take in all the Fortran 95 files, source files, and specify the output file as main. And then on the command line, it runs main. Now let's write Fortran in an older form of Fortran. So the first part is delete all of that. And then the second part is turn your caps lock on because Fortran is capitals only in Fortran 77. Now we're going to write a program that adds a couple numbers up. We're going to write a program that asks you to enter a number and then adds all the numbers from 0 to the number you put up and then put this output string down. Now that seems fairly straightforward, right? In Fortran, we're going to build a program that's going to sum some numbers. And at the end, we're going to finish the program.
It's blurry for everyone.
It is. So what I'm going to do...
You could maybe zoom in.
That's what I'm going to do. I'm going to make it bigger and zoom right in.
Alright, I can read that.
Let's go back here. Can you read that one?
Yeah, we can read that. Yes.
I can't share it like code, like VS Code.
Yeah. Maybe because it's on your webcam, that's not actually it's on stream.
Let's try. No, that's not gonna work. I'll just blow it up. I'll just blow it up stupid big. This program is not going to be long. We don't want long Fortran programs, do we? That big enough to read?
Yeah, here is that.
Okay. Column 6. So, in Fortran, the types of variables are dictated by the first character of its name. Integers start with the letter I. Right? When we want to output strings...
Is that an M? Is that FMT?
FMT, yeah. These are just single quotes. So the write statement here says write to, unit is which stream am I writing to, standard input or standard output? Those are the two main streams that we work with when we're working on the command line. The standard input device is your keyboard, the standard output device being your screen. And the format is a format string. And in this case, it's just given a wildcard and the data afterwards is the actual string. Now I said I need to read a number first. So after this statement, I need to read from standard input a value. And then the value I want to read. Now the reason I gave it a value at the beginning on line 2 there was because I don't want it to be undefined. If you run this program and just hit enter right away, it should have a default value in there. Now Fortran lets us have blank lines. That's cool. And I said my program was going to sum the numbers from 0 to whatever number I entered. From 0. And now I'm going to loop. From 0 to the starting value. So I'm going to add the count up to the starting value. And then in typical Fortran fashion, I have to put a label. And continue. That's a for loop. And now I have to write my output. It's all going to be on one line. And now I'm going to write the result. Oops. Keep hitting the shift key. Better. And sum. That's the whole thing. And from the little bit of assembly that you saw the other day, you probably can guess about how the Fortran compiler can turn this into assembly language. Maybe not exactly, but that's okay. You know, it creates a data element and sets a value, 6. Then it has a data element called enter a number, and it writes that out to the screen. And then it reads from standard input. In other words, it sits and waits until you put something on standard input. Now, with this emulator, standard input is right here. So I'm going to put the value 10 in there. I'll go back to my program. I'm going to open up the side window here, which is going to crush it a bit. and we're going to execute it. Sum of numbers up to 10 is 55. So that means you didn't type something correctly. Yeah.
Need to put command on the STD.
Standard input, yes. So on standard input, put whatever number you want. And then go back to the source code. Imagine writing a million lines of code like this.
Yes, that wouldn't be hard.
But we learn something every time we do some new programming language. One of the things we learn is that every loop in every programming language ever is a do loop. And we haven't done lots of, syntax and programming languages, but you're starting to play with it in C++ and C#, and we're going to do it pretty soon in JavaScript. I like that I go last in terms of introducing language concepts in JavaScript, because that way you've already seen them in C# and C++, and I can go faster. Right? But an interesting side note is that every for loop, every while loop that you do in every programming language gets turned into this basic construct: do something while true. Right? It's not running, Andre?
It's not running. I don't know exactly what you have.
Gonna guess you don't. Share it.
Share it?
Share it. Blow it up big. Yeah, you'll have to zoom in a little bit more. One more step. Control plus.
The spacing's off. The spacing matters, right?
The spacing matters.
Yeah, the spacing's one off. Like this one?
Yep. And the continue needs to come back underneath the D for do. Syntax error in write statement at line 1. So in the write statement, let's just start looking at the top one. Unit equals star, comma, FMT equals star. Single quote, enter a number, end with a single quote. Yeah. So take a look at all of the unit equals, format equals, make sure they're all set up the same way.
Oh yeah, you're missing comma on the read. Read? Oh yeah, I see that. I accidentally put this way. Right.
Okay. Now, part of the reason I like showing that stuff, don't feel bad about it, ever, okay? The more you look at code, the more it will look right to you. And so a lot of times having a buddy check your code is really invaluable. It's not like they're going to write your software for you, but they might point out obvious mistakes, things you forgot, things you mistyped. Just like the missing comma, right? Okay. So don't ever hesitate to have somebody buddy check your code. Right? It's a really good practice. A lot of companies force you to do it before you submit things into their source control system. So that's our Fortran stuff. Now, if you can imagine where I'm going with this, we're going to try a bunch of different languages out today. And we're going to take a look at how they actually work in terms of what they're doing. The way Fortran programs work is there's a Fortran compiler. And in this case, the GNU compiler is a compiler, assembler, linker all at once. When we use those three terms, there's three main processes that we're going through. The compiling process is about turning your original source code into assembly language. Now, eventually, you run into the problem that one file is not enough, and one module may not be enough. So when you start writing real programs that have real, actual guts to them that do something significant, writing it all in one file is very, very problematic. First of all, only one person can edit it at a time. The second is it's going to be super complicated. It's like going into C# and writing everything in one function that's 4 pages long. None of you would ever do that, but we have seen these kinds of examples. And when you start breaking things into multiple files, then you compile each file separately. And they generate some sort of intermediate files. And these intermediate files are what we call object files. They're just some sort of format that the compiler decided to create to store stuff temporarily. We then link them together. So compile, link, assemble, run. The compiler takes your source code and creates assembly language. The other thing it does in the background is that sometimes you will use names of things, variables, programs, functions, like the sum program here. It's called sum. That label or that tag will often be used in another file. Something has to resolve where the definition for that is. That's what the linker does. It goes through all of the intermediate files and finds all of the symbols that are used in the other files and makes a nice list for you. Oh yeah, if you want to call sum, that's in this file. Okay? Compile, link. The linker then squishes them all together and connects all the individual symbols from different locations. And then runs that through the assembler, and the assembler generates machine code for the particular processor you're on, and Bob's your uncle, you have a running program. And we rarely do those things in isolation. We rarely compile and then stop. We almost always compile, link, assemble, run. So most modern compilers, it's all one program. And they'll use command line switches on the program if you want to run just part of that pipeline. Okay. Now, those first compilers were built in assembly language. But once you have an assembly language compiler for one language, well, couldn't you use Fortran now to write a compiler for another language? And the answer is, well, of course you could, because you have a general purpose programming language. And this Fortran thing kind of started that craze going. In fact, every academic everywhere around the world working with computers said, wow, these are great, cool new machines. Let's build some new languages to solve new problems. And it kind of got crazy and out of control. In fact, you can flip through a whole bunch of these languages. The very first Fortran was built in 1957. COBOL followed quickly after. COBOL's specialty is doing business applications where you have a terminal, but you need to collect information from users. APL stands for A Programming Language. I know, innovative, right? And APL as a programming language is a math-oriented simulation language. Pascal and Forth are very English-like, and they were used to teach people programming early days. The Holy Grail happened in the early 70s, where Dennis Cunningham and Brian Ritchie invented the C programming language and the compiler to go with, which they then used to craft the first Unix operating system as part of their PhD thesis. That Unix operating system has C stuff so integrated into it that every Unix operating system these days has a C compiler built into it. Quite often they would distribute code to people, and get people to compile their own C programs. And most of the shell programs in Unix operating systems are actual separate programs. Want to do a directory listing? The ls program is an actual executable. It also saw the emergence of things like Smalltalk, which was the first truly object-oriented language. Smalltalk attempts to solve the problem of what happens when you have a million lines of code, how many people rewrite the same function over and over again? Because you don't know every function that's in there, and the names get really long so they don't collide with each other. Smalltalk tried to solve a lot of those problems by developing object-oriented software. Larry Ellison, an Oracle multi-billionaire, right, invented the structured query language and the relational database system. Up until about 2000, it was kind of the only game in town for large data stores and the way to access those data stores. In the 80s, Bjorn Strustrup took C the next step and added Smalltalk-like object-oriented constructs to the C programming language. He gave Smalltalk type properties to C++ classes and enabled us to use C++ to make large, robust, complex software systems. Ada was developed for the military in the US, and to this day, many of the US military programs are written in Ada. Python is literally named after Monty Python's Flying Circus. And it is a programming language that was designed by researchers who weren't necessarily computer scientists, but wanted to do some general purpose computing, and the notion of trying to write C++ just seemed really daunting to them. So they came up with an English-like programming language that had a lot of nice properties for manipulating data. And these days, Python is the language of choice for machine learning and artificial intelligence. Visual Basic was Microsoft's answer to the standard BASIC programming language that people learned to write programs in the first place. And part of the reason that Visual Basic exists and continues to exist is because Microsoft insisted that it was the scripting language of choice for its Microsoft Office tools. Java was built by Sun Microsystems when they still existed, and Java was a replacement for COBOL. I mean, originally it was designed to be a small, tight language that was write once, run anywhere. Java has this unique property of having to run on a Java virtual machine. So the Java code gets compiled in two steps. It gets compiled to a bytecode, and that bytecode is what you distribute all over the world. The link, assemble, run part is actually done by the Java virtual machine, and every different computer architecture has its own Java virtual machine. In this way, I can write a Java program and pick the exact same Java program and have it run on my Unix machine just as easily as my PC. Of course, coming out of that also came web programming languages like PHP and JavaScript. PHP bringing a preprocessor that happened on the server side. JavaScript runs in your client browser, and we're going to talk all about that, so I'm going to say not much more. C# was Microsoft's answer to Java, because you couldn't possibly have a language used on a Microsoft computer that wasn't built by Microsoft, used by Microsoft, developed by Microsoft, and supported by Microsoft. So Microsoft took Java, renamed it C#, and fixed the things that they saw problematic with it. The good part with C# is it's evolved over the years, and while it still just runs on Windows PCs by Microsoft for Microsoft, it has some really nice properties when it comes to building specific kinds of applications, particularly Windows desktop applications. Anyone know what Kotlin's for?
I know it's Android.
Yes, it's Android. Originally, Android was written in Java. Android is actually a flavor of Unix running on your Android device. And all the programs were written in Java. Unfortunately, as nice and easy as Java is to write programs in, it's also slow, like really slow. And for a small handheld device with limited processing capability, early Android phones kind of illustrated this. And it's interesting that they developed and adapted Kotlin to Android only when the phones got fast enough that they didn't really need it anymore. And an interesting side note is that Kotlin technically gets transpiled down into JavaScript, or into Java rather. So Kotlin becomes Java, and then that gets compiled. And then Swift is for iOS. Again, they started with an Objective-C language, which was a variation of C by Apple for Apple. And that Objective-C language was a little bit cryptic. They adopted Swift, which actually wasn't an Apple programming language. It was an open source language. But they thought it would do a better job of highlighting some of the capabilities in their devices. Now, with the exception of Kotlin and Swift, which the developers have put out there because they want people locked into their ecosystem, all of the other programming languages here, maybe not C#, are pretty much machine architecture independent. You will find all of these languages available on all of the hardware you work on. The ones we typically focus on today, the ones most games are written in, C# and C++, Unreal and Unity, and we do a bit in JavaScript as well because most of the live support, dev support tools are written to the web, and JavaScript works with the web. Let's take a 10-minute break. We'll come back at 10 after. And when we come back, we're going to go back into that old school programming teaching language, and we're going to do some stuff in one of these other languages that's a little more advanced than Fortran. All right? Okay. So just to get you a flavor of things, let's go back and do the exact same program we did in Fortran. But this time, let's do it in Pascal to see how the language kind of evolved over time. So this is about 20 years later, and how languages evolve. Now, with this compiler, this is the free Pascal compiler. I'm going to, again, delete the whole program that's there. It works the same way. You put the standard input.
This on Moodle again?
Yeah. Yeah. If you refresh Moodle, I've added a link to it. First thing is, there are no hard column restrictions anymore. And there's no capitalization requirements. Every line ends in a semicolon. Comments go in curly brackets. We declare things we're going to use. And at this point, we're starting to build programming languages that are defining things before they use them so that the things like the linker can go grab symbols more easily. You just have to remember those semicolons. Reading and writing to standard input and standard output becomes a lot easier. So read line is reading an entire line, not just a character from the standard input device. I have to write it back because otherwise I don't see what I've written. So just because you type some numbers into the keyboard doesn't mean they automatically show up on the screen. Spaces are just for readability. The compiler doesn't need them. Pascal introduced an assignment operator, the colon equals operator. And that was to distinguish in conditionals between assigning a value and testing a value for equality. And then we'll write our output. There's also no line number column width restrictions. So the programming language attempts to be very English-like in the way it operates, in the way it writes. Every statement ends in a semicolon. Begin and end blocks dictate single statements. In other words, the for loop takes a single statement. By using begin and end, I say the single statement could be multiple statements. The end of the program ends in a period, because, that's the way we write things. The sum of numbers up to number could be written all in one line as a write line with a couple parameters in it. And if I go pick a standard input number again, hopefully it will just run. And you'll notice it took a little bit longer to run this time. Gave me some comments. Here's the command line running the free Pascal compiler with main.pascal. And the other thing I'm thinking looking at all of this is, wow, I've had to blow this up really big so you could see it. Wouldn't it be easier if you actually kind of tried to do it on your own? So we're going to give that a try. If you refresh Moodle again, there's a link I put there to a plugin for your browser. And the plugin gives you what we call a secure shell, a command terminal that you can remote into another computer. I'm going to give you an address. You're going to try and remote into this other computer. Okay?
So just click add to Chrome.
Just add to Chrome. And it should come up with a little icon right beside the address bar. And when you click that little icon, it'll pop up with a pop-up dialog, and you'll click Connection Dialog. It'll look something like this. And when you collect, and when you click on New Connection, I want you to fill it in like this. The most important part being that IP address. That one.
It's hard to read the screen. And I'm not on this window that you're on.
Is that better?
Can I show you what I see? I'm pulling Chrome. It has an icon.
Mm-hmm. Yep. Yeah, that's right.
It is right, but
Yeah.
I can't. Nothing happens when I open it.
Nope, because you haven't set the parameters yet. So, under username or host name, yeah, Sliver's fine. Okay. The username, the next item down there, is VFS guest. All one word, all lowercase. And in the next tab over, you got to give it the IP address. The IP address is 50.68.116.27. Where it says home on your screen, Andre? No, not yet. Where it says home, you got to put in that IP address. Andre?
Yeah, I did.
Your screen stopped sharing? Yeah.
Did it freeze?
Yeah, that's okay. I'll just reload it. Cool. All right, give it a try. This is kind of experimental because we're not physically there. I'm going to close mine.
Just connecting. Connection refused.
Okay. Let's see if we can make it not refuse connection. Try again.
Yep. Password.
Password is the password is VFS, the number 4, and guest. I know it's really tough.
It says can't be established. ECDSA key fingerprint is a bunch of numbers. Are you sure you want to continue connecting? Yes. No. Fingerprint.
So, again, you connect VFS for guest. See if that'll connect you.
Yeah, connect it to your Ubuntu. What did you say the password was? And from that message, you have to type yes. I did that. What did you say the password was again?
VFS for guest.
VFS for. Yeah, so the number 4.
Yeah.
Okay.
I had to go switch something on here. It'll still let you connect right now.
Yeah, it doesn't type it. No, it just doesn't show it's typing. Oh. Just gonna hold back this. Type it and then just help you working. Oh. Okay, now it works.
Cool?
Oh, man. In the last line, the green line saying gas. Okay, so.
That is the command prompt. So, as you mentioned, yes, you're on one of my Ubuntu Linux machines. And just to be fun and cool, you're connecting through the internet through to my home, through a firewall, and onto a machine behind me. That guy.
You see your office now.
Yeah, I turned all the mess off. It's messy. There's crap everywhere. So, you need to ignore my office. Right. But that little computer in the background there with the screen on,
Yeah, you want to connect to that?
you are all connected to that through the internet.
That's cool. Hello, everybody.
Okay.
I can connect as well.
There we go. Okay. Is everyone able to connect?
Oh.
Now you will have the most problems, Arsene, because you're inside Vancouver Film School's firewall. But you should still be able to connect to a raw IP address. What does it say when you can't connect?
NaCl plugin exit with status code 250 connection refused.
Yeah. It's just the connection refuse part. So try and connect again.
I reconnected me, and I tried to choose another connection and start over.
Shouldn't make a difference. You want to share it when it doesn't connect? I want to see what it does. I'm kind of curious.
Well, just I'm on Discord from Mac. You can still work. Just share the screen. Oh, he's using two computers.
Yeah.
One for Discord and one he's working on. Yeah.
Yeah.
Oh, I can try doing that from Mac.
Yeah. It's more an experiment than anything else. When we're all on campus, I can pick a machine that's inside VFS's firewall and everything just works. And when everybody's outside of VFS, they can all connect through my home. I set up the network so it will allow it. And if you're poking at this yourself, if you have any kind of fun playing around with your network switch, the network switch that you have in your home can be configured with what we call a demilitarized zone. And essentially, you pick an IP address on your local network and you expose it to the internet in general. You don't ever leave them open for any length of time. So I'll tell you for a fact that by 5 o'clock today, this internet port will be shut. Okay? I'm kind of curious if you can get, like, Arseny is the only one inside VFS, so I'm kind of curious if VFS's hardware is what's getting in the way. It's got to go through two firewalls. It's got to go through VFS's firewall out and then into my firewall. Otherwise, you're just going to have to watch my screen.
Yeah, I think.
Yeah. So how many of you have used Unix systems before?
A little bit.
Just a little bit?
Oh, I used once. Like, maybe 2 years ago, we had a class.
So bring up a terminal on the Mac, because the Mac is Linux. And if you want to do a directory listing, it's ls to do a listing. If you want to change what directory you're currently in, you use the cd command and a space, and the parameter is which directory you want to go into. In your case, I'm going to suggest you guys go into the PG22 directory. If you type the command pwd, that prints the working directory and shows you what directory you're currently in. Why don't each of you make a folder to work in that's separate from each other? Granted, you're all logged in as the same user, but everybody can make a directory with the make dir command. And you can make a directory. I suggest using your VFS username. In this case, like I'll use PG22 Scott. Now, I've pre-built, if you want to go into your own directory, now if I want to clear the screen because it's getting cluttered, I'll just type clear. This is the command shell. This is one of the shell programs for Ubuntu. And just like the command interpreter on Windows, it takes a bunch of commands in, it has a bunch of environment variables, and it lets you run programs. If you type, if you type print env, it'll show you all the environment variables. If you want to do the same command over again, you can use the up and down arrows. It rolls through all your last few commands. So that was the last command I did, print env. All those environment variables are a variable equals and some value, and in particular, the same as on your Windows computer, the path environment variable tells Unix where to find programs. There's even a command called where. Where is the ls program? Can't find it. It's not in the path. Part of what the shell understands. Sorry. Which? My mistake. Where is on the Windows PC, which is on Linux. So as we experiment with this remote shell into a remote Linux machine, we can also see that I've got the free Pascal compiler just like we just used in the emulator here. And the only thing we're missing is an editor. Now, we can use the really old school editor, which is the visual interactive editor, which is on every Unix machine. I'm not going to make you use it. Right? The Vim editor has some idiosyncrasies. It has two modes. It has edit mode and it has typing mode.
Insert mode.
Yeah. And
what did you just do with this screen? Just type Vim.
VI. Technically, it runs Vim, which is a more modern version, but it's kind of the lowest level text editor on every Unix machine, and it's the thing you use, what would you say, David, as the last resort when nothing else works?
Hey, it's pretty good. What are you talking about? Yeah. Especially for if you're doing remote work over a server, you know they'll have this.
Right.
Something really.
Right. So what we're going to do is use VI. Oh, and if you're in there, the easiest way to get our Pascal program in there is to cut and paste it. So you hit I to go into insert mode, the letter I. Nothing looks like it changed. And then we go over to our emulator, select it, Control C, come back to our terminal, Control V to paste it. Control V to paste it? Nope. There we go. Just hit the right mouse button. That'll work. And if you want to save it, and this is the challenging part, you have to get out of insert mode, which you're going to do by hitting the escape key. And then you're going to give it a command. You're going to start that with a colon, and then WQ for write and quit. And it should ask you for a file name. No file name. If you're going to write it out, sum.pass. And the most interesting part to recognize is that many of the early C programs were written in editors just like this, with no syntax highlighting, no colors, which is why indentation became so important. If you want to save the file, go ahead. Hit escape. And then to enter commands, you use a colon. If you want to save the file, you go W for write, space, and then the file name. I just called it sum.pass. That'll save it as the file sum.pass. And then you can hit the colon again and go quit, Q for quit, and you get back. There's my sum.pass. All right, now we've got to make it, build it. So we have to figure out, how do we run the free Pascal compiler? And I'm just going to follow what we did in the emulator. Free Pascal compiler minus VW sum.pass. And it gives me some sort of linking error, but I'm going to ignore that. And the interesting part here you should note is there's 5, maybe 6 of us compiling on that little laptop all at once. Remotely through the internet, all over the world and back to my home. Back through my switch and router, back onto my little teeny tiny ancient laptop running Ubuntu. With 6 people connected, all doing it all at once. Kind of makes you wonder what that giant machine at VFS or under your desk is really doing. Right. Shall we try and run it? What you'll find is that there's 3 files there. The .o file is an intermediate file. It's an object file, which you could technically delete at any time. The sum with no extension is the actual program. And if we do a long listing, what you see is the Unix file system gives us permissions. And the way Unix identifies executables is not with a .exe extension, but just with the X for executable permission. The permissions on the left-hand side there you see come in 3 sets. There's user, group, other. User is the owner. That's VFS guest. Group is the second column over there, VFS guest. And the other is everyone else in the world. So this file has read, write, and execute permissions. Sum.o only has read and write permissions. Sum.pass only has read and write permissions. We're not going to get too crazy into setting Unix permissions. It also tells you how many bytes the file is, the date and time it was created. So to run it, you have to tell it what folder you're in Unix. So /sum, and I'm going to give it a number because actually, enter a number, 10. There we go. It's amazing, isn't it?
Pretty cool.
But at least if you can see it on your own screen, it's a little bit easier to read, right? Poor Arseny is looking at my tiny little blurry screen. Now, you got it on the Mac? Sweet. That's excellent. So every Mac is running Apple's version of Linux called OS X. And it's a very, very good, robust Linux implementation. Okay. There are, I don't know, David, how many, would you guess at how many different flavors of Linux there are out there these days? 20, 20, 30?
I think way more.
Way more?
Relevant ones probably around like
10.
20. But
Yeah.
There's a lot of irrelevant ones.
Right. So without getting into too much history, Kernighan and Ritchie built Unix at Berkeley, University of California, Berkeley. So that became the Berkeley Standard Edition. couple companies got a hold of it and said, wow, that's really good, but we can make it better. And they developed a consortium that created System 5 Unix. And those two flavors kind of split, and every different company had to build their own because it had to generate machine code for their processor, which is why everything had to be recompiled and rebuilt. Linus Torvalds brought the world back together again on Unix by creating Linux, which was a version of Unix that ran on Intel CPUs, which just happened to be all the PCs in the world. And as soon as he did that, a bunch of different consortiums, groups, free open software foundations decided that they could make better interfaces and better systems out of the Linux system, and they forked it off again in a bunch of different flavors. All right, before we leave this, let's do a couple more kind of things playing around with it. This command line is kind of the way things fit together. I'm going to kind of throw my slides up here on my screen again so you can see both. Most early workstations and program computers didn't have a windowing system, right? We would have, at best, multiple of these command terminals. And we would use these command terminals to run programs, to run jobs unattended. And the first games that came out were just text adventure games. People would write games that you would, which way do you go? North, south, east, or west? I go north. And it would parse your command and then display a paragraph of text of what you see and what you do. They're all built the same way. You write some source code in some programming language. You use the appropriate compiler to compile, link, and assemble for the machine you're on. And that modern build pipeline has stayed relatively unchanged since the mid-70s, mid-80s. Okay. That free compiler that we tried is just the latest iteration of the Pascal compiler. I've got a bunch of Unix commands in case you ever end up on a Unix machine. You can keep these as a reference. You can play around with them. VI, you really only need a few commands to get going. If you just type VI with a file name, it'll create a new file with that file name. There are some weird idiosyncrasies if you have to edit anything in VI. If it's long or difficult, you're almost better off finding a better editor. And once you're in a Linux windowed environment, there are lots of great editors out there, including you can get Visual Studio Code for Linux if you want to run on a Linux system. Now we made our little Pascal program compile and run. That command was really short and quick because it was only one file. And these commands generally run a little bit faster, or at least they appear to run faster than trying to use a Windows user interface or something. But behind the scenes, a lot of our development tools do exactly this. When you get into playing with Unity and you run a Unity program, it's literally creating a Unity command line that it runs in the background to compile, link, and build your Unity program and then display it in the editor. When you run Unreal and you push the play button in Unreal, it compiles, links, and builds by constructing a command line that it executes in the background that runs Unreal unattended, where it compiles and links your program. The same with Visual Studio. When you push the play button in Visual Studio, it's invoking a command on the command line, runs what we call a makefile, and generates your program. So all of our modern IDEs use this in the background, this command line option. If you're building a bigger program, the command line gets a little cumbersome. If you have to put 3 Pascal files on the same command line, that's one thing. If you have to put 150 of them and you make a typo, that's a little different. So one of the things we do is we invoke some tools to help us do this. All compilers and linkers work this kind of same way. We've got all the different files that make up our program. We run them through the compiler, which generates these intermediate files, and we assemble and link all of the pieces together into your execution, into your executable. On top of this, the operating system lets us redirect on the command line the input and output that we're doing. So for instance, when I ran the Pascal compiler, it had a bunch of output that it spit out, not the least of which was its license agreement and that linking error. And if I'm not around to see that, how do I collect that? So the operating system provides some tools to help us do that. It provides some tools to let us redirect standard input and output. So if I run that compiler again, but this time I want to capture the output, I'm going to redirect it, collect the output, and put it in a log file. And you can see that on my screen. You can just run it and then use the greater than sign to put it into output.log. Now, one of the lines popped out there, and that's because it's being written to the standard error output, not the standard output. And there are multiple different inputs and outputs that your programs can access. The standard error output could be redirected as well. But if I do a directory listing, I'll see I now have an output.log. Getting my DOS and my Linux mixed up. Cat is the Linux command to output a text file, to write it out to the screen. And you see my Free Pascal compiler listing came out in that output file. You can see down here. So redirecting our output can be useful sometimes. Like, let's say I want to find all of the things that have to do with Linux inside that output. Or if I'm writing something and I run it through the compiler and there are a bunch of errors, what I might do is redirect the output and go search for those errors. I can chain those things together. There are other programs to help us do some of these command line options. There's a command called grep, which is a general regular expression parser. I want to look for something. See if I can get the command right. So it can't find that. What about finding? So it doesn't know what lowercase Linux is, but it found the uppercase Linux. And I can glue these two things together, so I can run the Free Pascal compiler, and instead of piping it, redirecting it to output.log, I can pipe it and look for something. Right. So the vertical bar works as what we call a pipe. It maps the standard output of one program into the standard input of the next program. Now, where we typically use this stuff is where we're doing automated tools, where we might run a command that's going to have a really long set of output errors, and we pipe it into another command to search for the keyword error. So we just get a list of errors, and we redirect that to an output file. Or we pipe that to SendMail to send us an email of all the errors that happen. And all of this can be done automatically. All right. modern compilers do all this stuff for us, and a lot of times we're going to do this in programming languages like C. So let's turn around and do it on the Linux terminal again. There's a GCC compiler there as well. I think if we type GCC, it gives me a fatal error, which means it exists. So let's go create sum.c. Let's create this program in C programming language and see if we can't make it work. Now, anyone remember their standard C? Not C++, just C. Oh. Here comes sum.c. So if you check my screen shared, we're going to start. You can't use the cursor.
What's going on here? I'm trying to get out of here and just typing letters for you. I can't, like this.
So if you're trying to get out of there, you have to hit the escape key, then colon, then Q. And that'll get you right out of the editor. If you hit the escape key and you type I, that'll put you in insert mode, where you can start to insert from wherever the cursor is. You can't just use the arrow keys to move the cursor. Remember, this is just a terminal.
Even not letting me leave.
Yeah. So you'd hit escape, and then if you want to add to the end of a line, you can hit A to append. And once you're in append mode, just, don't make mistakes typing. Really old school C. I'll walk you through it in a sec. Long slashes, Scott. And then we'll put our output back together here. Leave that on the screen for a second.
Using arrow keys and messing it up?
Well, if you make lots of mistakes typing, this is a very punishing environment. It is not friendly.
Yeah, you type an arrow key and it gives you either A, B, C, or D. I know, I just keep doing that. I can't get out of the habit.
Yeah.
Completely screwed it as well.
Hitting the escape key and then going back into append mode helps.
Yeah.
So hit escape and then A, escape, A. Okay. Hit escape to get out, and then colon W to write it. Now, after seeing the Fortran and the Pascal version, I bet you can see what's going on here with most of this. There's a couple things that are a little weird, but other than that, it's not too crazy. The char star star is very old school. It's a pointer to a list of character pointers. Now, if you think about that, that's a list of strings. So on the command line, the first parameter is how many parameters are there? And on the second parameter on main, it's a list of strings. And stored in this super efficient way that stores just a single pointer to memory. When we get to the scanf line, it's asking for something in the format that has a decimal number. And it's stuffing it into the address of number, or the contents, whatever number is referring to. So that's that ampersand sign in there. The I++ is just a shortcut for I equals I plus 1. The sum plus equals I is something that C++ originated. And it just adds I to sum instead of saying sum equals sum plus I. And the very final printf statement has some formatting strings in it. Obviously, the %Ds are the formatting strings, and they get replaced with the parameters after it in sequence. And the /n is a new line. It's a special character that C programs run or understand. Now I'm going to run this through the C compiler. And see if it will do this without giving me a ton of errors. So already in function main, sum.c, line 20, column 1. Expected a semicolon before the final token. So now we got to go back and fix it. Right. I think that's what it is. Escape, colon, WQ, up arrow a couple times. Told me nothing. Created an output called sum, but of course that's what sum.pass created. Let's rebuild the Pascal one. And there's the listing of all the things it created. So now sum in Pascal at 177,000 bytes. Sum2 written in C at 8,400 bytes. The C compiler, just a smidge more optimized than the Pascal compiler. Yes? Just a little bit. So we can see the output here. We could try it. Let's try sum 2. Enter a number, 34, and it does the sum for us. And if we try the one written in Pascal, comes up with a different number. Why is that? How do they come up with different results?
Somewhere the math is wrong or different.
Right. This stopped one early. You get used to the finger keystrokes, believe me. Let's recompile and build it. And now it comes up with the same value. So the way it does for loops is a little bit different. Right. So the slides, it gives you the command line for how to build that application. Right. At the end of the day, all programs are kind of written in this pseudo-like English language, whether it's C or Pascal or Fortran or Kotlin or Swift or C++ or C#. Part of the reason we want you to see lots of different languages is to recognize that they're all kind of doing things the same way. It's just the keywords and syntax that change. They all get executed the same way. Right? And whether we run it in a simulator or we run it in a little test environment like this, the compiler, linker, assembler is all glued together these days. And they put our programs together for us. Now, with larger projects, you're going to have lots and lots of files. And keeping all those files straight and typing that GCC command on the command line gets really, really tedious really, really quickly. So that's where we start introducing command line tools to automate this process. We built the shell scripts to help us execute them to begin with, but when the shell couldn't really keep up with all these things, we created new programs that would take configuration files and use the configuration files to create the command lines for us. And the most obvious one that we use is what we call a makefile. And makefile is run by a program called make. Make makes programs. Now, a little bit of make is black magic, and we don't use make a lot manually these days, but you should see what they look like. This is a simple makefile. And if you look at the slides, you'll be able to see that it tells you the recipe for how to build application.exe on a Windows machine. And it's based on dependencies. In order to make main, you need app.exe. Oh wait, I don't have app.exe. How do I build that? Well, I need core.obj and extras.obj. And if I have those two things, then I can run the linker with the output of app.exe using core and extras. Now, core headers is another target we can build. Core.c, another target that depends on core headers. Extras.c requires core headers and extras.h. And at the very bottom, you see this general purpose rule. It says to build a .obj file from a .c file, run the C compiler with this option set and the parameter of the original .c file. So that generates the obj files, which will generate app.exe, which will generate main, which is what this makefile is trying to create. Now, as you can imagine, a complex makefile with hundreds of files and subfiles gets really complicated. We're not going to get crazy into the makefile part of it, but we would like to look at some of the command scripts behind them. And to do that, we want to look at the command line, particularly going back onto our Windows machines, because that's what we have in front of us. We're going to take a 10-minute break because we've been going for a little bit here. You can log out of my remote Linux system. We're not going to use that again. Okay. And when I come back, we're going to start talking about the Windows command line. And of course, we're going to give you another assignment to do. All right. So come back at 3:15. Two of me. All right. Next step we got to take. So we've looked at the compilers and languages and the way we typically execute them is through the command lines and all of the fancy user interface tools we have, from the IDE to the Unity and Unreal interfaces, all basically do the same thing. They generate a command line and execute that command line. We're going to take a look at that command prompt now, and we're going to start to do some things with that command prompt. Now, Windows provides lots of apps, and we can run most of these apps through command prompt. You can bring up a command prompt at any point in your Windows session with a bunch of different capabilities. If you haven't done it before, bring up a command prompt now. There's multiple ways to do it. You can use the Windows and R key to run and type CMD. You can bring up the File Explorer and go to the address bar and type CMD, and it'll bring up a command prompt at that location. So I'm just going to share the screen. I'm going to go here, key up CMD, and it runs the command prompt. This big fat guy right here. And in the command prompt, you have, much like the Unix commands, a bunch of commands you can run to see what's going on. It's another window into your environment. Now, if you want to adjust yours, you click here and go to Properties. You can adjust the fonts, the layout, and the colors of your command prompt. In addition to that, the environment that you get, you inherit, you type the word set, you'll get all of the environment variables that are currently set. Some of the commands here are a little different than Unix. CLS is the equivalent of clear, so it clears the screen. And we've got a few basic commands. So you should be in your home folder. Now, if you're on a VFS machine, like Arseny is, it typically puts you on the H drive by default, which is your home drive, on VFS's networked storage array, which is rarely where we want to work when we're working any of our game development tools, because now we have to transmit all of those files back and forth across that network drive. So you almost always want to work locally. The folder you see me in here is the home folder for me. On any given Windows machine, there is a users folder on the C drive. And inside that users folder, there's a folder for each user. That is the place you should do your work. If you type dir, you get a directory listing, and it shows you all of the folders and files there. And we've been through some of this stuff before. I'm going to give you an example of some things you should try on your command line. So go into your home folder and try typing dir and hit return and see what it brings up. And then try the next few commands here in a list. Try them all uppercase, try them lowercase. Try mixing them.
If anyone else other than Arseny has a Mac, instead of dir, you can use ls. We'll do the same thing on your terminal.
Nobody uses a Mac for real development, do they?
Whoa. You can say that in game dev, but we're in web. Well, actually, we're in operating systems. Never mind.
Anything weird happen?
I created a folder. Yeah, created my folder, but my other folder doesn't seem to create because separate lines.
So what did it create?
It created 3 folders inside.
And how do we feel about using spaces in file names now? Right. Now, when you look at all of the mess you've created on your desktop and in your home folder to date on your own personal computer, how many of those directories do you want to go clean up right now? Okay, avoid doing it, but your life gets significantly easier if you just stop using spaces in names. Use underscores, that's fine. Use capitals, that's okay. Don't use spaces. Right? And it all ties back to that command line. It's all because when we use a command line and when our programs generate command lines to use, those command lines typically don't handle those spaces very well. And when they do handle them, you have to put quotes and special kinds of quotes around things. And those quotes will often mess us up because we get a quote in the wrong spot. All right, here's something else you can do. Now it says to do this on your H drive. If you want to change drives on a Windows machine, you just type the drive letter. So if you want to switch to your D drive, you just go down there and you type drive letter. And it switches you to that drive. Now I'm going to do this all on my C drive. Okay, so the next thing you can do, I'm going to my little BFS folder here. I'm going to make a builds folder. Just like that. And then I'm going to change into that directory. And if I do a directory listing, I'll see only 2 files there. Those 2 files, they're there in Unix as well. Those 2 files are actual directories. They're named dot and dot dot. Dot dot is your parent directory, and dot is the current directory, the current working directory. So you can use them with the change directory command. I can change directory to dot dot, and that will change up 1 folder to my parent directory. Go back into my builds folder here. And from my builds folder, I'm going to use Notepad. You know Notepad. You run it from the start menu. Well, here we're going to run it from the command prompt. And I'm going to create this generate build.cmd. So the CMD extension tells Windows that this is a command interpreter that it's supposed to run. And when I do it, it's going to ask me, do I want to create a new file? I'm going to say yes, and it will bring up Notepad.
Einstein is not possible to localize the archive generate view.cmd. Do you wish to create a new archive?
An archive?
Not sure.
Pretty sure you didn't run.
New file.
Yeah, new file, yes. Yes, create a new file.
Okay.
Okay?
I was speaking of the Portuguese, so I was trying to translate it. Sorry for being.
Sorry for being from somewhere other than here. No, that's fine. Right? Just wait till you start getting all those menus in Unity.
Unity is fine. I'm used to just working English in Unity. So.
All right. So let's try something. Let's do a directory listing. So type dir there. And save it. File, save. And we go to our command prompt. And we see generate build.cmd here. Okay. So we started Notepad from the command prompt with a file name on the command line, which popped up an editor, which let us type stuff, which we saved in the editor, and now we can see the file. Now, to run it, we just type its name. And here's a trick. I don't want to type generate build, I'm lazy. The Windows Command Interpreter, if you hit the Tab key, will auto-complete if it can. Much faster. And it is the same up-down arrow feature as the command shell in Linux. And when I run generate build, what does it do? It executes the commands inside there. So let's do something a little more interesting. In my generate build.cmd, I'm going to go up one folder. I'm going to go up another folder. I'm going to do a directory listing of my home folder because I'm up to. Okay. And then I'm going to come back. I go back to the terminal, hit the up arrow to run it. Now it does a directory listing of my home folder.
Oh, that's cool. So it's following those lines and doing that in the command prompt.
That means if you have a command line that does something, you can do it over and over and over again, especially if you have a complex set of commands to do. Okay. You can put any DOS command in that command prompt. Okay. Any executable can be run, anything in the path. The sequence in which things happen is the sequence in which you show them in the file. And all programs are just a sequence of instructions from top to bottom of the file. And some of them, let you branch and loop around. And the command script is no different. It has comments. It has the ability for you to show things that are going on. You can test things, and you can branch. So go into that generate build.command and change it. Replace what you have there with what I've got here.
Generate build and change it to define.
Just delete what's in there, change it. It is.
Save and run again.
Yep. Now, the first thing is Notepad is probably the worst place to edit these things. Any other IDE will work. It's just a text file. Visual Studio or Visual Studio Code are just as good. So if you have them up and running, you might as well just use them. I believe they both have syntax highlighting for CMD files, or batch scripts, they're called. In this particular one, and if you look at mine in the Notepad here, and I'll flip it over into VS Code in a sec, it does a few things for us here. So first of all, you can use REM for a comment, or you can use the double colons for a comment. The percent signs, all the command line parameters for this generate build command get numbered as they come in. So if you put three parameters on the command line when you type generate build, like over here, if I go generate build, each of those parameters gets assigned to %1, %2, %3, respectively. So you can take multiple parameters in. In my script, I'm testing to see if %1 in quotes equals help in quotes. If there's no parameter, %1 is empty. So I have to put the quotes around it to contain it. And it'll say if, well, %1 is nothing, then if quotes are empty, then it's not equal to help. So it doesn't go to help, it just goes to the next line. And it says hello world. And then it goes to the end. So you can do rudimentary ifs and branches in batch files. Okay. Now, if you want to go a step further, I think we should. The first thing I'm going to do is I'm going to open this up in Visual Studio Code. So I'm going to close Notepad. I'm going to start up code. Visual Studio Code. There we go. And I'm going to open this folder. I'm just going to do this off the screen so that you don't have to see all the junk I have.
So like which folder or views folder?
Yeah. There we go. Now, this can get confusing with this much stuff on the screen, so this is where we could use the IDE's built-in terminal. So I can exit from this terminal and show the terminal in Visual Studio Code. And I can also show my generate build. That way I can just type on the terminal. I'm all integrated. It's my hello world. Cool, right? You notice it does the syntax highlighting for me? There's no real debugger for these batch files. That's the downside. So once they get to be longer than about a page, we have to move into more sophisticated tools, which is something we'll take care of when we get into the pipelines class. If you take a look at my slides here, you could run anything. Any set of commands that you could do, you could put in a batch file. And if you had a set of commands you could do over and over again, like build an entire build of a game, you could put that into a batch file, and then you could use the Windows Task Scheduler, for instance, to wake up your computer at a specific time every day and do some work for you. Okay? Whether it was something new to build, something to upload, something to compile, some new art to do. When these processes get more complicated, it is highly likely that you will forget or miss a step or mistype something. And instead of spending hours trying to figure out what you did wrong, you're better off trying to build an automated script to do this, so that once you get the script working correctly, you can always do it the same way, reliably. It also means that when it gets late at night, when you get tired, when you're getting close to a deadline, you could just run your automated tool to do the task you have to finish something up. So we're going to practice doing that. Okay. There are a couple new links in Moodle with the assignment. And the assignment is to build a command script. And what we're going to do with that command script is a couple simple tasks. Okay, so here's what I need you to do. And you're going to have to think a little bit to make it happen. It's not important that it's on your H drive, but I do want you to copy the demo app called Catching a Horse into your builds folder. So download it into your downloads folder right now. Also, download Studio Pose Olaf into your downloads folder. What I want you to do is to write a batch file, a CMD file, to copy the Catching a Horse file and the Studio Pose Olaf file into a builds folder under your drive, under your home folder. And then I want that batch file to find the number of vertices in the Olaf model. Okay? You get that? Download those two files from Moodle. Okay? They'll be in your downloads folder. It'll be users, your name, downloads. Write a command file. Have it live in your builds folder. Have it reach into your downloads folder and copy both of those files to where the command file is, to your builds folder. And then have that batch file find the number of vertices in Olaf. There's a problem to solve that can be solved with a batch file. You may have to do a little digging and learning.
How to check the number of vertices.
Yeah. If you find yourself trying to open up the model in Maya, you're going the wrong direction.
So you want us to create a thing that copies these
Mm-hmm.
and then paste them into the folder.
Right. So figure out how to copy files from one folder to another, and then find the vertices in Olaf.
What does vertices mean?
You figure it out. That's the kind of job you're going to get in the industry. Take a step back and understand the problem first. Look at all the pieces you got. Remember, the key and the hard part is find the vertices in OLAP and count them. Or rather, have your batch script count them. And part of what you'll have to do for the assignment is not just have your script, but you'll need to capture the output from your script. So your script should redirect the output.
We have to copy the demo and the OLAP from the download to the build.
Correct.
Properly.
Want the batch file to copy them. I want your command script to do the copying. If you need help, type help on the command line.
So it says to me on my Visual Studio Code, you don't have an extension for debugging batch. Should we find a batch extension in the marketplace?
You don't need it.
Yeah.
I just use Visual Studio Code because it's all in one. You could write this in Notepad and use the command prompt as well. That would work just as well. The trick is, what commands are you going to put in that generate build.cmd to copy files from your downloads folder to your builds folder? And then what commands are you going to use to find the number of vertices in OLAP?
bash extension. Just to be good.
Bring up a terminal and type the name of it. In VS Code, there's a button at the top called Terminal. It's a menu.
Yeah, open that.
So you open that, type in the terminal that pops up, type the name of your terminal. Make sure it's the CMD prompt and not the PowerShell prompt.
Yeah, it's the CMD, so I just type generate build in there?
Yeah.